Today we are going to discuss acceleration due to gravity. What is acceleration due to gravity and what is its expression? After that, we'll take variation of acceleration due to gravity on various factors like its dependence on height, how it varies with depth, what is its effect due to non-spherical shape of Earth, and finally we'll discuss what is the latitude effect or the effect of rotation of the Earth about its axis. So all these we'll discuss in today's discussion. Acceleration due to gravity is the acceleration with which the bodies are accelerated towards the center of the Earth. So if you consider any body, we'll find out what is the value of the force experienced by it, and then we can find with what acceleration it is directed towards the center of the Earth. So suppose we have Earth of mass m and we have a body of mass small m at a distance r from it. So the force experienced by this mass m due to Earth, that will be given as gmm by r square. Now if you consider what is the acceleration acting on this particular body of mass m. So acceleration due to gravity, this will be equals to F by m, because it will be force, that is mass, into acceleration. So this will be gmm by r square and this term divided by m. So this is your gm by r square. This acceleration due to gravity we represent with a small g. So the expression for g is gm by r square. This is when you take the body at a distance r from the center of the Earth. If we consider, if r is equals to capital R, that means we are taking the radius of the Earth as capital R. In that case, the value of g will be gm by r square. This is the expression for acceleration due to gravity acting at the surface of Earth. So this is the value of g. And accepted value of g, it is taken as 9.8 meter per second square. So the value of g, we take it as 9.8 meter per second square. This is the accepted value. For numericals and other, you can use this value there. But do remember that it depends upon this r. There are other factors also on which it depends. But of course, here in this expression, we can easily say that it depends upon the distance r. So obviously at different points, if you take that is on the surface of Earth or at some other point there, acceleration due to gravity will be different there. And as it is the acceleration, so obviously it is a vector quantity. So this is a vector quantity. And this will be acting towards the center of the Earth. Remember that in this expression, which we have taken, it is only the universal constant of gravitation, mass of the Earth and its distance term is coming. Or in this one, it is the radius of the Earth is coming. There is no term of mass of the body. That means the acceleration due to gravity will be same for all bodies kept at a particular point. Like here, instead of this m, if I'm using suppose the mass m dash, in that case, this will also experience the same value of acceleration due to gravity, because it is not depending upon the mass. As you are taking force per unit mass, so that mass term get cancelled, and this acceleration due to gravity then becomes independent of mass. Now let's take variation of g. How does acceleration due to gravity varies? It varies with height, it varies with depth, It varies due to non-spherical shape of the Earth. So from point to point on the surface of Earth, it will be different. And it also varies due to latitude effect or due to rotation of the Earth about its axis. So let's take first variation of G with height. So here, suppose if I assume that this is representing Earth, mass is m, and its radius is r. And suppose our point of observation is at a height h. So this radius is r and this is point here. And at this point, acceleration due to gravity is gh. Whereas on the surface of Earth, we assume that the acceleration due to gravity is g. So as we have taken that acceleration due to gravity is given as your gm by r square, where r is the distance from the center of the Earth. So acceleration due to gravity g, that is acceleration due to gravity on the surface of Earth. Expression wise, how much it will be? Gm by r square. This is g. If I now take acceleration due to gravity at a height h, so it is acceleration due to gravity at height h. So this will be written as your gm by r plus h whole square. Because you can see that now its distance from the center of the Earth will be r plus h. So it is your r plus h whole square. Now, suppose I call this as equation number 1 and this is your equation 2. So from equation 1 and 2, if I take gh by g, then how much it will be? Gm by r plus h whole square divided by gm by r square, and this indicates that it will be equal to r by r plus h whole square. So with that we can get that gh is g into r by r plus h whole square. Now you can notice that denominator here, if you consider r by r plus h, this denominator is large, so this fraction will be small. Therefore, acceleration due to gravity at height will be less than that on the surface of Earth. This we can easily understand from the basic relation also, that g is your gm by r square. So obviously, if r will increase due to increase of height, if h is increasing, r will increase. So if this is increasing, in that case, g will definitely decrease. So acceleration due to gravity decreases with height as the distance from the center of the Earth increases, and acceleration due to gravity is inversely proportional to a square of the distance. So that is why acceleration due to gravity will decrease as we move away from the surface of Earth. Now, as we have gh by g equals to r by r plus h whole square, so this can also be written as gh as g. Now this we can write 1 by h by r whole square. That means you can just think that we have multiplied and divided this fraction by r. In fact, r square. So in that case, it will be your 1 divided by 1 plus h by r. Now this term, if you take in the numerator, in that case, it can be written as your 1 plus h by r power minus 2. So this is gh. Now for a small h, we can take this gh nearly equals to g into 1 minus 2h by r. This we get it from the binomial expansion. Now what is that here? we are using 1 plus x power n expansion, power n expansion, it is your 1 plus nx plus higher terms of x. So this is nearly equals to 1 plus nx for a small x. Otherwise, you'll get here in the actual expansion 1 plus nx plus n into n minus 1 by 2 x square and higher powers there. So if x is a small, we can neglect x square term, x cube term there. So if you neglect, then it will be only 1 plus nx. But that is there only for a small value of x. So here also, if you consider for a small h, you will get this expression. So remember that this will give you directly the value of acceleration due to gravity at particular height. But we can use this formula only for small values of h. So this is applicable for a small h only. Like if it is asked at what is the acceleration due to gravity at 10 kilometer height, 5 kilometer height there, or 20 kilometer height. So there you can use this formula. Remember, this fraction has to be small. So small means with respect to what? This is definitely with respect to radius term. So that means h should be small with respect to radius of the earth. Radius of the earth is 6400 kilometer. So in respect to that, if you are taking a small values of h, definitely you can directly use this formula. Otherwise, this is the general formula that we can use for any value of h. Let's take the second factor on which acceleration due to gravity varies there, that is the depth. So suppose if you consider that this is earth, its radius we have taken as r. We want to find acceleration due to gravity at a depth d from it. That means from its surface, we are taking a depth there, which is d. So d is this one. And acceleration due to gravity at that point, if you consider, suppose it is your gd. Gd is acceleration due to gravity at this point. So what we do, we take an imaginary sphere inside earth so that the particular point where we want to find acceleration due to gravity at certain depth, it lies on its surface. So suppose this is the depth d at which you want to find acceleration due to gravity. So taking that particular point on the surface of a sphere, we construct or imagine an imaginary sphere there. Obviously, what will be the radius of this one? This radius will be equal to r minus d. And suppose its mass we assume as m dash. M is the mass of the earth. And m dash is the mass of this shaded part. That means now you can imagine as if the earth is made of two parts. One is a solid sphere of radius r minus d, so that the particular point is on its surface, and other is the outer shell of that, which has a thickness which will be equal to d. So in this case, suppose gd is acceleration due to gravity at depth d. So this is acceleration due to gravity at depth d. Now this is given as gm dash by the radius, that is your r minus d whole square. Now here just you have to think, for acceleration due to gravity, what we have taken general formula there, that was your gm by r square. If you use this one, in that case, if r is decreasing, because now as you are going inside earth, the distance from the center will decrease. So it will appear that this g should increase. But when we go inside earth, the acceleration due to gravity instead of increasing, it decreases. Now, why it decreases? Because not only this r is decreasing, but there is a change in the value of m. This m here we consider as the effective mass. So this is not the mass of the earth. So this is your m dash. And what is this m dash? This will be the mass contained in the imaginary sphere of radius, which is your r minus d, so that on the surface of that the particular point is located. Why we are taking this m dash, or we are taking effective mass, not the mass of the entire earth there? Just because for the particular point where you want to find acceleration due to gravity, the field due to this thick shell will be 0. So it will be only the mass contained in this inner sphere that will be playing effective role in the acceleration or the force on the particular body kept at that point, not the mass contained in this outer shell. That is why we take only the effective mass there, that is your m dash. Now, if I assume that Earth is made of uniform material, that means its density is same everywhere, it is uniform, having uniform density. So if we assume that it has uniform density, in that case what we can take? Mass per unit volume. It is your m by 4 by 3 pi r cube, that is m is the mass of the earth and r is the radius of the earth, so mass per unit volume is this. How much will be the volume of this inner sphere? That is equals to 4 by 3 pi r minus d whole cube. So now this is a mass per unit volume multiplied by the volume of this inner sphere, that will give you mass of the inner sphere there, or that will give you the effective mass m dash. Now this term, if you divide by r minus d whole square, so what you will get here? This will be gm, that will be the term. Now this 4 by 3 pi will get cancelled, and here it is your r cube and r minus d. This term will be left. Now again one r if I take inside, so that we have now gm by r square, it is 1 minus d by r, and this is your g into 1 minus d by r. So this is your gd. So this is the expression for acceleration due to gravity at a depth d, where d is the depth, r is the radius, and g is the acceleration due to gravity on the surface of earth. So this expression we can use. Now here in this one, if I consider if d is equals to 0, what does it mean? The point of observation is on the surface of earth. If we take the depth 0, it means the point is already on the surface of earth. So if I substitute it here in this expression, what you will get for gd? It will be your g into 1 minus 0 by r, and that is g. And of course, if you take the acceleration due to gravity on the surface, it is definitely g. Second case, if I take d equals to capital R, that means where is the observation point? It is at the center of the earth. So here it will be at the center of the earth. So gd will be the g into 1 minus r by r, and that is 0. This is indicating point is at the center of earth, and this is indicating point is at the surface of earth. So on the surface of earth, acceleration due to gravity is g, but at the center of the earth it will become 0. Remember the earlier formula which we have taken for acceleration due to gravity at certain height, and especially the formula like gh, which we have used as g into 1 minus 2h by r. this formula which we have used, or we have got GH equals to G into 1 minus 2h by r. This was applicable only for a small h, but this is applicable for any value of d. So this is for only a small h, only for a small h, but this is applicable for all values of d. And what does it mean? That means the d should vary from 0 to r. So it is applicable for all values, but this one is applicable only for a small value of h. There is another form in which this acceleration due to gravity at certain depth we can find. That expression, if you consider, suppose we assume that acceleration due to gravity inside Earth when we are taking, this is at a distance r. That means this which we have taken as r minus d is basically, suppose it is your distance r. So this is given as your g m dash by r square, where this r is basically r minus d. So in this case, here g by r square will be there. If you are assuming that Earth has uniform density and the expression is given in terms of the density rho, we have derived in the previous derivation there, or previous form you can say, density as your m by 4 by 3 pi r cube. But here if it is given that if rho is the density of Earth, so in this case this m dash will be given as your 4 by 3 pi r cube into rho. This will be another way in which m dash can be expressed, especially in form of the density there. So here if you substitute, in that case what you will get? 4 by 3 pi g rho into r. So this is the acceleration due to gravity at particular depth there, which is at a distance r from the center of the Earth. So this is another form in which it can be expressed. One question which is often asked there, to plot the nature of variation of acceleration due to gravity with distance. Basically, it is the plot of variation of g with distance. Here, if we take that this is x-axis is there where we are taking the distance, and on y-axis we are taking acceleration due to gravity. So we know that up to the radius of the Earth, g is varying directly to r. So if this is your r, up to r it will vary directly. So it is g is directly proportional to r. And after that it will vary inversely to a square of the distance. So g is varying inversely to a square of the distance when r is greater than capital R, that is the radius of the Earth. So this is the plot of variation of g with distance. Next factor, that is your variation of g due to non-spherical shape of Earth. Earth is not perfectly spherical in shape. It is having a shape where it is flattened at the pole and bulged at equator. So if you consider now, this is suppose the equator, radius is suppose RE, this is representing the pole, and here the radius is suppose RP. This is your equator, this is representing pole, and here suppose the acceleration due to gravity at pole, we take it as your GP, and on the surface equator it is your GE. So just by going by the expression mass of the Earth, if I assume it capital M, so acceleration due to gravity at pole, this will be equals to GM by RP whole square. This is acceleration due to gravity at pole. So this is your G at pole. Similarly, G at acceleration due to gravity at equator. If I represent this as your GE, it will be your GM by RE whole square. Now, if you consider the ratio of GP and GE, this is your GM by RP whole square, GM by RE whole square, which is RE by RP whole square. Now, as RE is greater than RP, you can see it is flattened at the pole and bulged at equator. So definitely polar radius will be smaller than equatorial radius. So if you substitute it here, what you will get here? That GP will be, in fact, GP by GE. This will be greater than 1. RE is greater than RP. So this will indicate that GP will be greater than GE. So acceleration due to gravity, it will be more at pole than at equator. Remember what we have taken earlier? We have taken that we are moving away from the surface of Earth. So with height, acceleration due to gravity was decreasing. Why it was decreasing? Because the distance from the center of the Earth was increasing. And acceleration due to gravity is inversely proportional to a square of the distance, especially if you are taking outside the surface of Earth. In the second case, if you go inside Earth, that not only the effective mass of the Earth is decreasing, but also the distance from the center of the Earth is also decreasing. But the effect of mass will be more prominent as compared to the separation, that is the distance from the center of the Earth. That is why acceleration due to gravity ultimately decreases there. But when we move on the surface of Earth from one point to other, then also it varies because of the non-spherical shape of the Earth. So as polar radius will be different from equatorial radius, or at other points also it will be different there. Obviously, if you move from on the surface of Earth, the acceleration due to gravity will be different at different points. Maximum we can notice there at the pole and equator. Let's now take variation of G due to latitude effect or due to rotation of Earth about its axis. Now here, suppose we assume that this is Earth, this is the axis about which it is rotating, this is the axis of rotation, and suppose omega is its angular speed of rotation about its axis. Now here, if we assume that Earth has got perfect spherical shape, we have in the previous case we have discussed due to non-spherical shape of the Earth. Here, even if we assume that it has a perfect spherical shape, it means the distance is same on the surface of Earth from the center. But as Earth is rotating about its axis, and this is suppose the equator. Latitude when we take, that means we take suppose the particular point P here. If you join this point to the center, the angle which it makes with the equator, that is your latitude, and that we represent it by lambda. So as the Earth is rotating about its axis, so every point which is on the surface of Earth is also rotating about this axis of rotation. So what will happen? This particular point will also execute a motion about the axis, and its path will be something like this. If I assume that the capital R is the radius of the Earth, this one has the radius, suppose a small r. So small r is the radius of the orbit in which this particular point mass at a latitude lambda will be rotating. So acceleration due to gravity, if I assume that it is g, so g will be acting directed towards the center. But that is not, that means if I consider g as the acceleration due to gravity, in that case the weight will be your m into g. So weight will be acting towards the center. If I assume that we have a point mass m here at this location. But now it is not only this weight, but due to the rotation of the Earth about its axis, there is the centrifugal force also acting on this particular point. This centrifugal force will be given as your m omega square r. So basically you can assume what we have taken, that this is point, this is the Earth, weight is acting in this direction mg, and due to its motion about the axis of rotation, centrifugal force will act in this direction, m omega square r. So this body will experience force. One, its weight due to attraction of the Earth towards its center, and also the centrifugal force which will be acting on it. So the resultant of that, if suppose it is in this direction given by the parallelogram law of vector addition there, if I represent it as the mg lambda, this you can call it as the apparent weight, because this is arising only because of the rotation of the Earth about its axis. And how much will be this angle? This is your lambda. So how much is this angle? 180 minus lambda. So now if you consider mg lambda, this is equal to the vector sum of the two forces there, that is its actual weight, and the due to latitude effect you can say that centrifugal force which is acting. So this is your mg whole square plus m omega square r whole square plus 2 times mg into m omega square r and cos 180 minus lambda, and the whole term's power will be half. Now if you consider this particular triangle, here we have a small r by capital R. This is equals to cos lambda, because if this angle is lambda here, lambda is here, so this angle is also lambda. So in this triangle, cos lambda will be equal to a small r by capital R, and that gives you a small r equals to capital R cos lambda. This we can substitute here in this expression. So if you put it here, it is your mg square plus m omega square. For r we are putting capital R cos lambda whole square. Then it is your, here it is your cos 180 minus lambda. So it will be your minus cos lambda. So this we can write it as your minus 2 m square g omega square capital R cos lambda. And for this one again you will have cos lambda term there, and the whole term's power will be half. It is the square root of this term. Now suppose we take a mg square common. So here it is your mg square if you are taking common, but it is your square root term here. So ultimately it will be mg term which will come out. This will be, first term will be 1. This will be your omega square r cos lambda by g whole square. Then this is your 2 into omega square r cos square lambda by g power half. Now you see this particular term omega square by g, this is the quantity which is very small. So as this is very small, we can neglect the higher powers of it. So neglecting higher powers of omega square r by g. Here it is first power, but here it is your square. So obviously that higher powers like this particular term we are neglecting. So if you neglect it, in that case you will get here mg 1 minus, now this term will be there, 2 omega square r cos square lambda divided by g, and the term's power is half. Again, we have taken this term to be very small, so obviously we can again use binomial expansion there. So this is nearly equals to mg. 1 minus power will come here, so half into 2 omega square r cos square lambda by g. Why? As omega square r by g is very small, so we can substitute it here. And now if you just expand or remove the bracket here, then in that case you'll get g minus omega square r cos square lambda, and this is your g lambda, because m we can cancel from both sides. This was basically your mg lambda, so m we can cancel from both sides. G lambda will be equals to g 1 minus omega square r cos square lambda, and if you are removing this bracket, in that case this g will get cancelled, so you will get g lambda equals to g minus omega square r cos square lambda. So this is the expression for acceleration due to gravity at a latitude lambda. Now you can see if lambda is varying, cos lambda will vary, so g lambda will change. If omega changes, omega is the speed with which Earth is rotating about its axis. So if omega changes, again this g lambda will change. So this is the expression for acceleration due to gravity due to latitude effect. If you multiply it by m, you will have mg lambda equals to mg minus m omega square r cos square lambda. This is now we call it as the apparent weight. This is the actual weight, and this is basically called as the latitude correction. So you can see from the actual weight some quantity is subtracted. This quantity m omega square r cos square lambda is the term which is getting subtracted. So obviously the apparent weight will always be less than the actual weight. One more thing you can observe, if you consider at equator, lambda is 0. So in this case, apparent weight there will be equals to actual weight minus m omega square r, because cos lambda, if you put for lambda 0, then in that case it is your cos 0, which will be 1. So this will be the expression. Whereas at pole, lambda is 90. So in that case, apparent weight will be equals to actual weight, because this term will be 0. So at the pole, apparent weight is equals to actual weight. Here, many times it is asked there, if Earth suppose stops rotating about its axis, what will happen to the weight of the body? We have seen in the general expression that apparent weight is less than the actual weight due to this latitude correction. So if it is said that Earth stops rotating, it means omega is 0, so Earth will stop rotating about its axis. So the quantity which we are subtracting will not be there. So apparent weight will become actual weight. So what happens to the weight of the body if it is asked? Normally we tend to say that weight of all bodies on the surface of Earth will increase, because earlier it was less. But the correct statement is weight of all bodies on the surface of Earth will increase except for the bodies at pole, because at pole already it was equal to the actual weight. So if Earth stops rotating, there will be no change in the weight of the body there. So it will remain equal to its actual weight. So this is the discussion on variation of G on various factors.